Hello. In this lecture, we'll talk about isoperimetric inequality of simple closed curve in R2. So what does this isoperimetric inequality tells? So suppose if you take a simple closed curve in R2, so it compares the area bounded by that simple closed curve and the length of that curve. Okay. Okay. So let us begin. Yeah. Okay. Uh, so let us first give you the statement of this isoperimetric inequality. Then I'll explain uh, all the things in details. Okay. So let us take, so let gamma be a simple closed curve in R2. Okay. So suppose you have this curve which is simple and closed in R2. Okay. And so this curve, so it will bound a region. So it will bound this region. Okay. So now if I take this region and take the area of this thing, so the isoperimetric inequality, it tells you that, so area of the region, so which I call it to be interior of gamma. So this is less than equals to 1 by 4 pi length of gamma and square of it. Okay. And this equality holds if and only if this gamma is a circle. Okay. So suppose if I take a circle, so if I take a circle and suppose the radius of the circle is r, so this radius is r. So this is my, say, C. So area of this interior of the C, which is this region. So this is equal to your 4 pi r square. Okay. And length of C is equal to 2 pi r. Okay. Yeah. So therefore here, so this area is equal to exactly length of C square divided by 4 pi. Okay. So yeah, so what we are going to show that, so this area of this region is less than equals to square of the length of this curve divided by 4 pi. Okay. And equality occurs if this gamma, it becomes a circle. Okay. So in order to prove this thing, so we'll be needing some theorem like Green's theorem, Whittinger's inequality. Okay. So first we'll go through that thing and then we'll come to the proof of this isoperimetric inequality. Okay. So let me first state Green's theorem. So let us take two smooth functions over R2. So f and g be two smooth functions defined on R2. Okay. All right. And let us take, so let gamma be a positively oriented, means the orientation is given anti-clockwise. So positively oriented, simple, closed curve in R2. Okay. So then, so what is Green's theorem? So it tells you the following. So if you take this double integral over what? Over this region. Yeah, so I have taken this orientation. So if I take this region, so if the double integration is taken over this region, over this del gx, so it is the partial derivative of g with respect to x minus del f del y dx dy. So this will be equal to, so this will be equal to the, so this line integral. So this will be equal to this line integral. So this is Green's theorem. Okay. So now using Green's theorem, so what you can see, so now let us take, so let fx equal to, fxy equal to half of y, and gxy is equal to half of x. Okay, so if we put these functions in this equation, in this above equation, so what we'll get, so this integration, now del gx minus del fy, so this will be equal to your 1. Okay, so here it should be minus. So then del gx minus del fy, it will be equal to your 1. So this integral, which is nothing but by the definition of the area, so this is area of the region bounded by this gamma. So this area is equal to this double integral, and this will be equal to your x dy minus y dx, and you have half of this. So this line integral. Okay. All right. So we'll be using this formula of this area. Okay. All right. And now let me state, so the Whittinger's inequality, which will be required to prove the isoperimetric inequality. So what is this Whittinger's inequality? So let f be a real valued function, be a real valued smooth function such that, so f of 0 equal to f of pi is equal to 0. So then the claim is, so integral 0 to pi df dt whole square dt is greater than equal to 0 to pi ft square dt. Okay, and this equality holds if and only if this ft is equal to d times sine t, where this t it belongs to 0 pi. So for some constant t. Okay, so this is Whittinger's inequality. So how to prove this thing? So proof it is like this. So let us take a function. So let gt is equal to, so this function f gt is defined in this way, ft divided by sine t. So gt is this defined in this way, and then what you can check is the following. So this is exercise. So check using this. I mean, you have to do integration by parts. So using that thing, so that you can check that. So integral 0 to pi df dt whole square dt is equal to 0 to pi ft square dt plus 0 to pi dg dt whole square sine square t dt. Okay. Okay. So once you show this thing, so therefore, so clearly, so this term is always greater than equals to 0, because inside the integral, it is the term is greater than equals to 0. So this is always greater than equals to 0. So this will imply that, so this will be greater than equals to 0 to pi f t square dt. Okay. And suppose you have this equality is equal to this. So this will imply that this term is equal to 0. So this term is equal to 0. And again, the inside part is greater than equals to 0. So it will imply that that this dg dt it is equal to 0. And also the converse is 2. So dg dt is equal to 0. So this implies that gt is constant. Okay. Okay, all right. So we have proved this Whittinger's inequality. Now, using this, we'll be proving the isoperimetric inequality. Okay. So let us take. So let gamma be the arc length reparameterization of the curve gamma. Okay. All right. And also note that because this curve is closed, so gamma 0 is equal to your gamma L. All right. Okay. Okay. So now, so in R2, so we have this simple closed curve gamma. So suppose, so this is my gamma. Okay. So now, what we can do, so we can apply a translation. And suppose this is my gamma of 0. So we can apply a translation so that, so this gamma, it starts from the origin. Okay, so we can apply a translation so that, so this curve, it will be something like this. Yeah. So if I apply a translation, I can move this gamma here. Okay, so such that, so this gamma 0, it comes to your origin. Okay, so without loss of generality, I can assume that gamma 0 is equal to 0, 0, because translation, it is an isometry of R2 and it preserves area as well as length. Okay, so without loss of generality, so assume gamma 0 is equal to this origin. Okay, and so now what we are going to do, so we'll change the arc length parameter. So let S be the arc length parameter. Okay, so and let T, so we'll define another parameter. So let T equal to pi S divided by uh, length of gamma. Okay, so this means length of, or maybe in short, I'll just write L gamma, which means, so L gamma, so is length of gamma. Okay, all right, and yeah. So again, so you can reparameterize this gamma in T, and we'll again name the reparameterization as gamma only. Okay, all right. So now, so this gamma, now it is here, it passes through origin, and now we'll be using the polar coordinate. So let us take, so let x is equal to r cos theta and y is equal to r sin theta. Okay. So here, so what I want is the following. So we want this curve to be also regular curve. Okay. So this, I think I have not written. So let gamma be a simple closed curve in R2, and gamma is also regular. Okay, so let us assume this thing. Okay, so we are taking this polar coordinate. So this this my gamma. So gamma t is xt comma yt. So xt yt, it is point on this gamma. Okay, and so I am taking the polar coordinate. So xt, it will be rt cos theta t, comma yt rt, sorry, yt is equal to your RT sine theta t. Okay. So in polar coordinates, so gamma t is this thing. All right. Okay. So now, so what is area of this interior of this gamma? Okay. So this is equal to half of yeah. So this integral x dy minus y dx, so which is nothing but equal to half of 0 to pi x dy dt minus y dx dt. Okay. So now you know that this, so this is in fact xt, yt, and here you have this dt. Okay. So now xt is rt cos theta t, yt is rt sin theta t. If you plug this thing here, so you'll get this is equal to your, so half of this integral, half 0 to pi r square d theta dt. Okay. So you have this thing, area. And now if I check, if you check this thing, so dr dt square plus r square d theta square. So this will be equal to your dx dt square plus dy dt square. So you can check this thing. And this is equal to dx ds square plus dy ds square multiplied by ds dt square. Okay. Okay. So now, so this is equal to, yeah. So this ds dt is equal to what? So this from here, so you can get the length of this gamma. Okay. Yeah. So now note that. So what is this first thing? So gamma with respect to s, it will be a unit speed curve. Okay. So unit speed curve means, so this square, it will be equal to your 1. Okay. So therefore what we have, so this 1 multiplied by, so ds dt square. Okay. And s is given by this equation. So s is given by this equation. So ds dt square is what? So ds dt square is length of gamma square divided by this pi square. Okay. So therefore, so this will be equal to, so this will be equal to length of gamma square divided by pi square. Okay. All right. So now let us take this thing. So length of gamma square divided by 4 pi square minus this area of this interior of this gamma. Okay. This will be showing it is greater than equals to 0. Okay. So this, again, it is equal to the following thing. So it is, yeah. So from this equation, so what we have, so from star, yeah. So length of gamma square. So what I can do, so if I take 1 by 4, 0 to pi, dr dt square plus r square d theta dt square dt. Okay. So if I take this thing, so we'll get this length of gamma square by 4 pi s, 4 pi square. Okay. minus, so what do you have? So area of this interior of gamma. So this is half of this integral 0 to pi r square d theta dt dt. Okay, so you have this thing here. Okay, and so this will be equal to 1 by 4 times this integral 0 to pi r square, not r square, dr dt square plus r square d theta dt square minus twice of r square d theta dt whole times dt. Okay, so you have this integral here. Okay, and so let us take, so let I be this integral. So I is this integral, and what we'll do, we'll split this in two parts. Okay. Uh, okay. So this is equal to 0 to pi uh, r square d theta dt minus 1 whole square dt plus 0 to pi dr dt square minus r square dt. Okay, so I you can write like this, and so suppose this is my, this integral is I1 and this is my I2. Okay, so note that both yeah, so first of all, this I1 is greater than equals to 0. So note that, so I1 is greater than equals to 0. Okay, and what about I2? So here we apply this Rödinger's inequality. So I2 is 0 to pi dr dt square minus r square dt. Okay, so this is greater than equals to 0 by Rödinger's inequality. Okay, so therefore, so what we have, I is greater than equals to 0. Okay, and so I is equal to 0. So if and only if, so both I1 and I2 is equal to your 0. Okay, so this, if I take I1 equal to 0, so what we have, so this I1, if I take it to be equal to 0, so then the inside part of this integral, it will be equal to 0 because it is a non-negative thing, and it will be 0 for all t. So it will imply that so this d theta dt minus 1 is equal to your 0. So this will imply this is equal to your 1. So this implies that theta is equal to t plus alpha. Okay, and I2 equals to 0. So this will imply that so this dr dt, so it is equal to RT. So R, it is a function of t. Okay. Yeah. So sorry. So this there's one mistake I have made. So I2 equals to 0. So then again by this Whittinger's inequality, so it will follow if RT is equal to some A times sine of T. Okay, so this again by Whittinger's inequality. So for some constant, okay, for some constant A. Okay, so therefore, so this RT, so this is equal to A times sine theta minus alpha. Okay, so this is the polar equation of circle passing through origin. Okay, if you take this R2 plane, and so this equation, so it gives you the polar equation of, so polar equation of circle is RT equal to A times sine theta T minus alpha. Okay. All right. So therefore, so what we have shown that, so this implies that, so this curve gamma is a circle. Okay. So therefore, we have proved this isoperimetric inequality. Okay. All right. So we'll stop here.